Welcome to the pilot action of the new Metro project. The new Metro project aims to identify and support skilled workers in fourth-generation industry with an emphasis on training needs and emerging skills across Europe. As part of the project, the Laboratory of Knowledge and Intelligent Informatics of the Department of Informatics and Telecommunications of the University of Ioannina, as a project partner, created a training activity to develop skills around the Uppaal unit. Introduction. Uppaal is essentially a toolbox for verification of real-time and embedded systems developed by Uppsala University and Aalborg University. It has been applied in a plethora of areas ranging from communication protocols to multimedia applications. Here we describe the networks of time automata used in Uppaal. We provide the description of the tool. We give an example of its utilization. Timed automata in Uppaal. The Uppaal model checker resides on the theory of timed automata. Its modeling language provides additional features such as bounded integer variables and urgency. The query language of Uppaal, used to specify properties to be checked, is a subset of TCTL, timed computation tree logic. In this part of the presentation we give the modeling and the query languages of Uppaal and we provide an explanation of time and timed automata. The modeling language. Networks of timed automata. A timed automaton is a finite-state machine extended with clock variables. It uses a dense time model where a clock variable evaluates to a real number. All the clocks progress synchronously. In Uppaal, a system is modeled as a network of several such timed automata in parallel. The model is further extended with bounded discrete variables which are a part of the state. These variables resemble to programming languages. They are read, written, and we can conduct arithmetic operations. A system state is given by the locations of all automata, the clock values, and the values of the discrete variables. Every automaton may trigger an edge on its own or synchronize with another automaton, in order to move to a next state. The modeling language. The figure above shows a timed automaton modeling a lamp. The lamp has three states locations: off, low, and bright. If the user presses a button, synchronizes with press, the lamp is turned on. If the user presses the button again, the lamp is turned off. However, if the user quickly presses the button twice, the lamp becomes bright. The user can press the button randomly at any time or not press the button. The clock Y of the lamp is used to indicate whether the button has been pressed quickly, Y less than 5, or slowly, Y greater than or equal to 5. The modeling language. A timed automaton is a finite directed graph with conditions over and resets of non-negative clocks. In the previous example, y:0 is the reset of the clock Y, press, and press. Denote action co-action, which is the channel synchronizations. Timed automata sometimes consist of a network of timed automata over a common clock set as well as actions. In the next slide we give the timed automata extension provided by the additional features of the Uppaal modeling language. Timed automata in Uppaal. Templates. Automata are given including parameter set that can be declared in any type, for example, int, chan. These parameters are substituted an argument in the declaration process. We can declare constants as const name value. They cannot be altered and given an integer value. We also have the bounded integer variables, which we can declare as int min, max, name, where min and max bounds. Guards, invariants, and assignments can include expressions with a range of bounded integer variables. The bounds are checked in the verification process and a potential violation leads to an invalid state that is not considered at runtime. Timed automata in Uppaal. Binary synchronization channels are declared as chan C. In order to synchronize an edge with another one, the former is labeled with C, and the latter C. A synchronization pair is selected in a non-deterministic manner if several combinations are enabled. Broadcast channels are declared as broadcast chan C. As the broadcast dictates, a sender C may synchronize with a number of receivers C. Note that the broadcast sending is never blocking even if we have no receivers. Urgent synchronization channels are declared by prefixing the channel declaration with the word urgent. Delays are prohibited in a synchronization involving an urgent channel. Edges using urgent channels for synchronization cannot have time constraints. Timed automata in Uppaal. If we use urgent locations, we essentially add an extra clock X, that is reset on all incoming edges, and possessing an invariant X greater than or equal to 0 on the location. Tush, when we have the system to an urgent location, we cannot allow time to pass. Committed locations impose more restrictions than urgent locations. A state is committed if any of the locations in the state is committed. A committed state must not delay its operation, and the next change must comprise an outgoing edge of at least one of the committed locations. Arrays are allowed for clocks, channels, constants, and integer variables. We can define them by giving a size to a given variable, such as JMC5, clock 1, int 3,9, U6. Timed automata in Uppaal. Initializers are encapsulated to initialize arrays of integers and integer variables. Record types are declared with the struct similarly as in the C programming language. Custom types are given using the C-like typedef construct. You can define any custom type from other basic types such as records. User functions can be defined in a global or local manner to templates. Template parameters can be accessed from local functions. Expressions in Uppaal. Select. A select label includes a comma-separated list of name, type expressions. Name is a name of a variable. Type is a defined type. These variables can be accessed by the associated edge only. They will obtain a non-deterministic value within the range bounds of their types. Guard. A guard is an expression satisfying the following conditions. It is side-effect free. It evaluates to a Boolean. Only clocks, integer variables, and constants are referenced, or arrays of these types. Clocks and clock differences are only compared to integer expressions. Guards over clocks are essentially conjunctions. Disjunctions are allowed over integer conditions. A guard may call a side-effect-free function that returns a bool, although clock constraints are not supported in such functions. Expressions in Uppaal. Synchronization. A synchronization label is either on the form, i.e. test, or is an empty label. The expression must be side-effect-free, evaluate to a channel, and only refer to integers, constants, and channels. Update. An update label is a comma-separated list of expressions with a side effect. Expressions must only refer to clocks, integer variables, and constants, and only assign integer values to clocks. They may call functions. Invariant. An invariant is an expression that need to adhere to the following conditions. It is side-effect-free, only clock, integer variables, and constants are referenced. It is a conjunction of conditions of the forms greater than or equal to E, where X is a clock reference and E evaluates to an integer. An invariant may call a side-effect-free function that returns a bool, although clock constraints are not supported in such functions. The query language. Uppaal as a model checker need to verify the model. Similarly to the model, the requirements specification must be provided in a formally well-defined and machine-readable language. Several such logics can be found. Uppaal uses a simplified version of TCTL. Like in TCTL, the query language comprises the path formulae and state formulae. State formulae is given to provide individual states, whereas path formulae quantify over paths or traces of the model. Path formulae can be classified into reachability, safety, and liveness. State formulae. A state formula is an expression that can be evaluated for a state irrespective of the model behavior. Like I == 7. The syntax of state formulae is a superset of that of guards. A state formula is a side-effect-free expression. In contrast to guards, the use of disjunctions is not restricted. It is also possible to test whether a particular process is in a given location using an expression on the form PL, where P is a process and L is a location. In Uppaal, deadlock is given using a particular state formula. The formula simply comprises the keyword deadlock and is satisfied for all deadlock states. A state is a deadlock state if there are no outgoing action transitions neither from the state itself or any of its delay successors. Due to current limitations in Uppaal, the deadlock state formula can only be used with reachability and invariantly path formulae. Path formulae, reachability properties. Reachability properties ask whether there exists a path originating at the initial state, such that a state formula phi is eventually satisfied along that path. Reachability properties are used for sanity checks, i.e. communication protocol. These properties do not ensure the correctness of the protocol, i.e. that any message is eventually delivered, but they can validate the basic functionality of the model. In Uppaal, this property is written using the syntax C is different from 0-phi. Path formulae, safety properties. Safety properties are stated in the form of something bad will never happen. A variation of this property dictates that something will possibly never happen. In Uppaal, these properties are formulated in a positive manner, like something good is invariantly true. Let phi be a state formulae. In Uppaal we write A, phi and E, phi, respectively. Path formulae, liveness properties. Liveness properties essentially dictate that something will eventually happen. The more useful form is the leads to or response property, which is read as whenever phi is satisfied, then eventually psi will be satisfied. For example, whenever a message is sent, then eventually it will be received. In Uppaal, these properties are written as A different phi and phi, greater than psi, respectively. Time issues, guards and invariants. Uppaal uses a continuous time model. We may use guards and invariants to control the delay of the transition and execute a property. For example, if we want to loop until x less than 3, invariant, and x greater than 2, guard, to perform a reset. Note that if we remove the invariant, the behavior changes since we have another condition on the guard. There are cases that deadlock may occur if we perform this action. Time issues, committed and urgent locations. There are 3 different types of locations in Uppaal: normal locations with or without invariants, urgent locations, and committed locations. The location marked U is urgent and the one marked C is committed. The clocks are local to the automata, i.e., X in P0 is different from X in P1. Time issues, committed and urgent locations. An urgent location is equal to a location with incoming edges resetting a designated clock Y and labeled with the invariant Y less than or equals 0. Time may not progress in an urgent state, but interleavings with normal states are allowed. A committed location is more restrictive, in all the states where P2.S1 is active. In the previous example, the only possible transition is the one that triggers the edge outgoing from P2.S1. A state having a committed location active is said to be committed. Delay is not allowed and the committed location must be left in the successor state, or one of the committed locations if there are several ones. Example, the train gate. We have a railway control system that controls access to a bridge for several trains. The bridge is a critical shared resource that may be accessed only by one train at a time. The system is defined as a number of trains and a controller. A train cannot be stopped instantly and restarting needs time. Therefore, timing constraints exist on the trains before they enter the bridge. When approaching, a train sends a P signal. Thereafter, it has 10 time units to receive a stop signal. This allows it to stop safely before the bridge. After these 10 time units, it takes further 10 time units to reach the bridge if the train is not stopped. If a train is stopped, it continues its way when the controller sends a go signal to it after a previous train has left the bridge and sent a leave signal. Example, the train gate, train template. Train, the model of the train is given in the figure below. Example, the train gate, train template. The train template has 5 locations: safe, upper, stop, start, and cross. The initial location is safe, which means that a train is not approaching. The location has no invariant, which means that a train may stay in this location an unlimited amount of time. When a train is approaching, it synchronizes with the controller. This is accomplished by the channel synchronization upper. On the transition to approximately, the controller has a respective upper. The clock X is reset and the parameterized variable E is set to the identity of this train. This variable is used by the queue in the controller to determine which train can continue or which trains need to be stopped. Example, the train gate, train template. The location upper includes the invariant X less than or equal to 20, which dictates that the location needs to be left within 20 time units. The 2 outgoing transitions are guarded by the constraints X less than or equal to 10 and X greater than or equal to 10, which corresponds to the two sections before the bridge, can be stopped and cannot be stopped. At exactly 10, the two transitions are enabled that enable us to take under consideration any race conditions if there is one. If the train can be stopped, x less than or equal to 10, then the transition to the location stop is taken, otherwise the train moves to location cross. The transition stop is also guarded by the condition E equals it and is synchronized with stop. When the controller decides to stop a train, it decides which one, set C, and synchronizes with stop. Example, the train gate, train template. The location stop does not possess an invariant. A train may be stopped for an undefined time. It essentially anticipates the synchronization go. The guard D equals it ensures that the right train is restarted. Here, we assume that a train may receive a go synchronization even at the point that it is not idle, fact that will provide a non-deterministic restarting time. The location start includes the invariant x less than or equal to 15 and its outgoing transition is constrained by x greater than or equal to 7. This means that a train is restarted and reaches the crossing section between 7 and 15 time units non-deterministically. The location cross resembles to start, since it is left between 3 and 5 time units after entering it. Example, the train gate, gate template. The controller initiates in the free location and it checks the queue regarding its state. If the queue is empty, then the controller anticipates approaching trains with the synchronization. When a train is moving towards the gate, it is placed in the queue with the add synchronization. If the queue is not empty, then the first train on the queue is restarted with the go synchronization. In the OC location, the controller anticipates the moving train to go out of the bridge, leave. If other trains are approaching, they are stopped, stop, and added to the queue, add. When a train moves away from the bridge, the controller removes it from the queue with the rem synchronization. Example, the train gate, the queue template. The queue includes one location start where it is anticipating instructions from the controller. The shift down location is used to compute a shift of the queue. This template uses an array of integers and handles it as a FIFO queue. Example, the train gate, the gate and queue template. Verification. We can check for reachability, safety and liveness properties as well as for the absence of deadlock. We provide an example of each. Reachability, egate.oc. The gate can receive and store messages from approaching trains in the queue. Safety, a. Gate.add1 or gate.add2, imply queue.len n1 where the locations add1 and add2 are the only locations in the model from which add is possible. Liveness, train1.ipr, train1.cross, whenever train1 approaches the bridge, it will eventually cross. Deadlock, a. Not deadlock. Conclusions. We showed some insights on timed automata and how they are used in Uppaal. We showed the modeling language. We presented expressions and other features of Uppaal. Finally, we showed an example of practical significance that comes with the tool. References. Acknowledgement to Gert Behrman, Alexander David, and Kim G. Larsen, Department of Computer Science, Aalborg University, Denmark. Thank you for your attention.